Today I'm here to talk to you about energy production forecasting using AI/ML weather models. In a departure from much of the other talks, I'll be focusing less on the subsurface, but looking at the atmosphere. Let me begin with first a motivation about why we did this work. Now, understanding ambient conditions like temperature, pressure, humidity, wind, precipitation conditions are useful in optimizing operations across a range of things in the energy industry. Whether you're operating an oil rig or a power plant or a refinery, these are the kind of conditions that affect how the way you run things. Specifically, renewable and conventional energy production methods are strongly affected by weather conditions. The capability of forecasting days and weeks ahead helps a lot with trying to understand risk assessment for many of these things, as well as trying to understand how you price energy. Traditional numerical weather predictions, as well as downstream applications, such as computational fluid dynamics model for understanding how energy is produced in wind farms, these are generally computationally intractable for real-time operations and forecast. In reality, we are constrained by a number of things when it comes to these kinds of predictions. That is the fact that these observational data comes in every few minutes, and you want to be able to run these predictions. Now, if it takes you 7 days to run a prediction of what happens over the next 7 days, then by the time it's done, it's just about useless. So the idea here is trying to do things fast and iterate quickly. And here, specifically in this work, I'll try and demonstrate a modular workflow for fast ensemble AI/ML weather simulations with wind energy production models as a downstream output to understand how energy is produced. So this is the high-level workflow diagram of what we're trying to do here. We begin by obtaining operational and historical data on weather conditions. We then run a weather prediction for the next period in time. So this could be an hour, this could be 6 hours, depends on the type of prediction or ML inference that we are trying to do. We do want to run some level of numerical weather prediction. Europe's integrated forecast system, for example, runs every 6 hours. Same with the US GFS system. We need this to calibrate our ML surrogate models, which we build based on our historical data. For example, the ERI5 reanalysis data set, which includes all of the variables associated with the weather conditions. How we want to predict far into the future is by using things as in an autoregressive manner. That is to say, to run the ML model to get the outputs, feed that as initial conditions into the next set of runs in order for us to predict far into the future. For example, for medium range weather forecasting, this could be 7 days, it could be 10 days, or even beyond. Once we have this, it's not that we can immediately run our downstream applications. For example, trying to understand how the wind farm works and how to run the simulation of trying to understand the energy production. We have to post-process these outputs. We have to clean things up. We have to get some data assimilation going on, and with that, we can then run our wind farm simulation. Once we do that, we want to optimize our operations to maximize the energy output. At the end of the day, this allows us to forecast what's going to happen over the next 7 days and how exactly this affects the energy production. I do want to emphasize that this is just one example of a downstream application. The idea here is to be able to expand this well beyond this. For example, if you want to understand how a combined cycle power plant works, the same type of a workflow should apply. And that's why we look at this as a modular problem. The other thing is this itself is sort of represented as a directed acyclic graph. If you think of this as a computational workflow, you're bringing together a lot of different pieces. And you want to be able to swap out some of these pieces depending on what type of simulation you want. And I'll touch upon this later. But I do want to take a step back here and try and explain to you how these new AI/ML technologies are changing the way we do weather modeling. Now, traditional methods, they depend on, for example, the direct solution of these types of physics equations. I do want to caveat this by saying that there are lots of other AI/ML technologies that are going into this type of even traditional numerical weather forecasting. But here, the limitation is that this does take hours to run. For example, like I said, every 6 hours you get one of these forecasts for over the next 7 to 10 days. Now, we are at a tipping point here whereby AI/ML weather models are proving to be more and more reliable, sometimes even exceeding the accuracy you'd get from high-resolution numerical weather forecasts. They are indeed trained based on observational data as well as in a data-driven approach, but also assimilated data that is based on the numerical weather predictions. The key thing here is that these types of models run within seconds to minutes on HPC resources for the inference. It can take hours, it can take days, it can take weeks to train, depending on the type of data sets you're using. But at the end of the day, once you've done that, you're capable of running these large-scale ensembles for probabilistic forecasts. And this is the key thing. To be able to run in real time thousands of concurrent ensemble simulations allows us to get a more accurate forecast than if you were just trying to do a deterministic prediction. So I'd like to talk about some of the examples of these AI/ML models that have come out recently. We've worked on some of this ourselves at Amazon. For example, the Earth Former model, which is a vision transformer for precipitation nowcasting. Recently, in the last NeurIPS conference, we released PREDIF, which is a precipitation model, again, which uses a denoising diffusion operator similar to what you would see in these generative AI algorithms like Stable Diffusion. But we've really just focused on the precipitation nowcasting piece. There are other methods out there, ForecastNet based on the NVIDIA Modulus framework, GraphCast, and Pangu Weather. And it's key to understand that these three really focus on the medium range weather prediction, that is expanding out to the next 7 days to the next 10 days and trying to understand how the weather conditions change over this time. It's key to understand that these ML models span spatial and time scales. So the resolution themselves, it could be 1 degree, it could be 0.25 degree. We have to understand that we're talking in the time scale and the length scale of kilometers here and hours. And the key to getting value out of these types of ML models is the capability to run ensembles and probabilistically get forecasts and insights from there. And I'll show some examples of this. But going back to my earlier point, weather is something that affects a lot of different things. Specifically on energy production, I'm going to focus on wind farms, but just the same thing could be extrapolated. For example, cogeneration, combined cycle power plants, temperature, pressure, humidity affect how your gas turbine or steam turbine efficiency evolves. And if you have a part-loaded power plant, then you definitely want to take these things into consideration and how to optimize your operations. Same thing with solar farms. Precipitation nowcasting and forecasting allows you to figure out how you want to run these farms to maximize your energy output. And finally, downstream of this, with the grid and distributed energy resources, the power demand and supply. The one aspect of that I will not be covering today is really the demand piece. This shifts based on your weather patterns. If it's too hot, then you want to run your air conditioning. Electricity demand goes up. Same thing, if it's too cold, you want to run heating. And all of this, at the end of the day, affects how you decide to price your energy and predict how this is going to evolve in the next week or so. I just want to talk a little bit about the requirements and how we end up architecting a framework like this. Not so much specifically on how it's done on AWS, but some of the key things is this is really an event-driven workflow architecture. So you do need some type of workflow orchestrator like an Airflow or something like this, which allows you to basically run your autoregressive rollouts, your inferences. Based on the outputs of those inferences, you want to trigger more inferences. And at the same time, take those outputs, you want to analyze it, do a bit of post-processing in another set of functions, and then finally take that and run the next set of CFD simulations, for example, for a wind farm. And the key thing to understand is all of this happens on heterogeneous compute. So cloud is one of the ways you could implement this. For example, you want GPU instances to run your ML that has become the de facto standard. But then again, some of your other analysis may not need such powerful GPUs, and you may want to run it on cheaper, say, CPU instances. But the key thing that comes out of many of these algorithms is a lot of data. So for example, in the numerical thought experiment case study that I'll show today, even just running a 1,000 member ensemble ends up outputting within the next set of cycles of predictions about 0.5 terabyte. So you can imagine over the course of a day, you're going to get tens of terabytes, hundreds of terabytes, and this just keeps accumulating in terms of your predictions, which you may want to look back on and try and analyze. And another key thing is if you look at this and consider that all of this needs to be done before you get your next set of observations, the automated observational systems for surface measurements, for example, it comes in every 20 minutes. So you want all of this to be done and be ready for the next set of observations to trigger the next set of events in the workflow chain. So in order to do our weather forecasting for the medium range problem, we choose to use the NVIDIA Modulus framework. I won't go too much into this. I do know tomorrow there is a workshop on this specific topic. But I will stop with saying that the Modulus framework is a toolkit for us to solve partial differential equations using machine learning methods. Specifically, the method used here is Fourier neural operators. If you were to solve this in a 2D domain, you can also solve it on a sphere. A spherical harmonic transform analogously applies. Adaptive Fourier neural operators are enhanced also using another method. For example, you could use a vision transform, which is what is being used right now in AFNOs. And there is a distinction between the variables that are called diagnostic, which is really downstream, and precipitation is something that comes out of the model. In order for you to do an accurate prediction, you need to look at the prognostic variables or the primary variables. So in the modulus framework in ForecastNet, for example, there are two different models. So one that does the prognostic piece, the baseline model, as well as the diagnostic model. And this has been trained on the ERA reanalysis data, the one that I mentioned from the European Commission for the Medium Range Weather Forecasts. So let's look at the scenario we are considering here. We want to do ensemble forecasting with 1,000 members, just as an example to understand how exactly the computational workload balances and to see the modular workflow. We want to do this across 7 days, so this involves running 30,000 inferences. And this is done with each one of those time intervals being about 6 hours. We initialize this using unseen data from ECMWF ERA5, the same data set that I mentioned before. And in order to understand how exactly this uncertainty propagates throughout the, both the ML model for the weather, but also downstream of this and how this affects the production of energy inside the wind farm, we perturb the system. In this case, we do uncorrelated noise generation with a Gaussian random field in order to inject a little bit of noise and see how this propagates into your weather predictions. We know that it's sort of a chaotic system. That is, the tiniest of input perturbations results in a large change over time. So we just want to see how that affects the uncertainty downstream. So we see the results of our first scenario, which is on top you'll see the 3 plots, which are your U10, your velocity at 10-meter height, and here the other component of velocity, V10 at the bottom. Now across the ensemble members, even running this across a 7-day, which is quite a long time frame, we see that there is good agreement over most of the regions. There are some regions of high heterogeneity. I'll touch upon that later. But there's also qualitative spatial correlation, not only between the velocity members, but if you were to plot the temperature at 2 meters or the mean surface level pressure, you'd see that all of them correlate in this deviation, the standard deviation, which is the deviation from the ensemble mean, which is what we see on the right-hand side. Now the ensemble standard deviation, again, to highlight, is highly heterogeneous around some strongly localized weather events. We could correlate this, for example, for a storm front or hurricane that's passing through one specific area. But also interestingly, it corresponds with local geographic features, for example, where land masses are. So one idea is to also incorporate the local topography, the geography of the regions into these models in order to get more reasonable predictions and more accurate predictions. It's highly sensitive to the method and scale of perturbation, as you can imagine. We use uncorrelated Gaussian random noise, but if you were to use pink noise or some other method, then you might get, and you do get some other insights from it. Let's look at the results for the medium range forecasting across the ensemble. We see that zonal wind, which is what the variable that I was talking about, the velocity at a certain height, like 10 meters, has a significant variation in this ensemble that is done in this autoregressive way across for the 7 days. For example, here you see we started with June 1st, so after 5 days, we start seeing a significant fluctuation in these velocities. One important thing to remember is if you just blindly run an ensemble simulation and average the results to think that you get a more accurate result, this may not be physically consistent. You need to do something that's a little bit more rigorous because, for example, it doesn't satisfy conservation laws, something that's easy to see for the velocities. There has been some recent work just coming out from the Caltech group who came up with this ForecastNet idea about scale-aware spatial correlation for the perturbations, and this allows you within a Bayesian model uncertainty framework to calibrate your model to understand how exactly noise affects, perturbations affect the evolution of the system. Let's numerically quantify what this looks like in practice. So we pick a certain location. For example, this corresponds to the wind farm that I will talk about in a bit, and plot the velocity across time. We see there to be sort of 2 different time scales acting here. One that spans the first 3 days, and the other is a diurnal cycle. So there are these 2 different phenomena that's happening at the same time. Over the first 3 days, the velocity magnitude is rather low. And then it starts growing, and this is when also the noise starts amplifying. And the final velocity magnitude, as you can see at the end of 7 days, is wildly different between the ensemble members. Let me just now switch focus to the other application, which is taking in the inputs of this weather simulation, and that's the wind farm simulation piece. There are, of course, many different methods of running these wind farm simulations. Our requirement here, even starting with the small ensemble size of just 1,000 for the weather, is we have to run 300,000 of these wind farm simulations within that 20-minute period, which then leaves us with no choice but to work on the lower fidelity side of things, which is semi-analytical models. So here we use a velocity deficit wake model, which has been calibrated against large eddy simulation CFD results, as well as wake measurement data. Interesting enough, given the noise in the wake measurement data, some of these simpler analytical forms or semi-analytical forms do show really good agreement for these simple cases. And this is all done with a wrapper with PyWake, which is basically an open source toolkit for modeling wind farms at reduced order. So this is the scenario that we're looking at. The location itself is based on a real wind farm, Hollandiscoot Noord. It's just off the coast of the Netherlands. We put 64 turbines in a grid. We don't arrange it in any sort of heterogeneous manner. We just use a simple equidistant circle for this one. And we set it up with active yaw control, so it realigns to match the direction of the wind. Two things that I do want to highlight coming out of the weather model, which is the fact that the outputs cannot just be directly taken and interpreted, because the hub height for these turbines is not exactly at 10 meters. It's obviously much higher than that. And one of the things I will highlight in a little short while, which is the fact that across the heights, we basically need a super resolution. That is to say, we need to understand how the velocity changes with height. Primarily, right now, people are using empirical models such as this power law one here, with a constant tau, which is calibrated, for example, for stable air over the ocean or over a landmass, and that really changes the value of tau. One thing we want to look at is using a machine learning model which takes into account the local geography, the topology, and uses that and other weather conditions, and uses that to understand how exactly the height variation in velocity happens. The other thing is wind itself is not constant over any time period. There are gusts and there are periods of calm. So we use statistical sampling in order for us to predict at shorter time intervals what exactly the wind could be. And we use this to run a series of simulations. So this is the results of what we see. Over the first 3 days that I've mentioned, unsurprisingly, the wind velocity is lower than the cut-in velocity, or velocity in which it makes sense to run the turbines. But once this crosses, the outputs themselves grow, and you can also see the standard deviation in the outputs grows. So with this, we're able to get a measure of the uncertainty in this type of a model that comes all the way back from the noise that we introduced in the weather model. So for us, there's also a potential correlation with the time scales of the different weather phenomena, so we can relate this back to how exactly the situation evolves. And here we see there's a sort of plateau to about 9% deviation from the cumulative mean, if you're to look at the total energy production over the course of the week, which is what we are plotting here. Let me talk about some of the limitations of the methods that we're using. The first thing is, with many of these models like ForecastNet, the small version of it gives you a 1 degree resolution. The high resolution version gives you a 0.25 degrees, but at the end of the day, this still relates to tens of kilometers. We want to go down to the level of kilometers, or if not even more, which requires some type of super resolution mechanism. We also want to capture these statistical variations in wind over time, which is something that definitely happens in nature. And having a machine learning or other type of data-driven model would be significantly useful for this. Also being able to recalibrate it on the fly based on observations, because there are lots of different observation stations placed around which do stream in outputs in real time. Now the wind gradient across height is a big limitation, as I was saying. The model is empirical, and this is something where we're looking at developing some type of machine learning models based on drone observation data, working with our internal teams. And the other thing is having an ML model that's purely data-driven, does not include sufficient physics-based constraints. So perhaps we can look at injecting some of these into the physics-informed methodology. I do want to quickly summarize, which is that we've started with a survey of the ML models. I presented 4 of them for weather nowcasting and forecasting. We've used ForecastNet. Again, there is a workshop on Modulus tomorrow that goes into more details of the underlying technologies, the mathematics, and the implementation. We've used it for ensemble modeling here, And we've done a quantitative numerical analysis, not so much a theoretical analysis, of the uncertainty through this 7-day forecast. And our weather prediction analysis has been done through reduced order model because of the fact computational cost. We do hope that there will be a day when you could run exawind and these high fidelity blade resolved models at higher speeds, in which case we could easily just use some of those outputs to calibrate some of these reduced order models. We understood how uncertainty propagates all the way from the noise that we've injected into the weather system to the energy production forecast and numerically quantified that. And future applications may involve combining lots of different ML models or with traditional HPC simulations and in sort of an event-driven workflow which automates the entire process, because you have lots of, it's really a problem of high throughput compute. You have hundreds of thousands of different models running, interacting, and triggering each other. And to be able to do this on cloud architecture is really a bit of an enabler. And this can be done across different industries. Specifically in energy, there are so many different pieces that we could put together in order to do, for example, energy production forecasting. With that, I'd like to thank you, and I open the floor to any questions.
Thank you, Vidya. Questions?
Oh, yes.
Hi. Yeah, in the beginning you said the accuracy is even better than physical or numerical simulation, right? But then at the end you said that the machine learning is not considered some restriction from the, so which one is it then?
No, this is a really good point. So specifically when it comes to weather modeling, we are reaching a bit of a tipping point in which we observe that in some cases, the IFS or the GFS, which is a numerical weather prediction models, are just as good, or the ML is just as good as these types of numerical weather predictions, but that doesn't mean that it's reliable, or that theoretically you can show that these data-driven models supersede these traditional classical physics-based things. Especially on the wind farm side, of course, you can never replace these high-fidelity blade-resolved sort of CFD simulations, but on the ML side, no, we're getting there with weather, and I would say that that's the first case when you see this huge transition whereby a pure ML model can match up to numerical weather predictions.
Quick question for you on the AWS reference architecture.
Yeah.
On the storage piece.
Yeah.
You called out S3. I'm just curious to see if you guys were using Glacier Instant Retrieval or Deep Archive or one other particular tier in particular to accelerate?
Oh, you could certainly, those are long-term storage. This is something that happens in the matter of minutes.
So was it Glacier Instant Retrieval you guys were using?
Oh, no, just the standard tier. Yeah, because Glacier is really, if you want to store it for a long time, maybe you do want to store this for a long time. You want to store the observations and some of the IFS predictions over a long time because you want to go back and analyze it. That's how the ERA5 was built in the first place. But with regards to the ML predictions, I don't know if you want to store that over the course of months or years. So probably it doesn't make sense to put it in Glacier.
Yeah, I did see you talk quite a bit about weather modeling, coupled with computational fluid dynamics and stuff. Do you have any ideas in terms of how you are going to help your customers with physics-based simulations or digital twins per se, right? That was one of the things that you said is missing. Maybe that's going to create a more accurate prediction of performance of wind turbines.
That's right, because you have lots of wind turbines, you have lots of sensors, they're collecting a lot of data, temperature, pressure, humidity, wind speeds, etc. Being able to recalibrate a model on the fly to match that would be fantastic. That involves additional architectural considerations because you're now streaming all this IoT information. Correct. And then on the fly, you're recalibrating the constants that go inside your reduced model, et cetera. So
okay,
that would be the next step.
Do you have like some partners that you're already working with in terms of physics-based modeling or coupling it with physics aspects of things?
Well, we're not, but we're happy to explore.
Okay, thank you.
Okay. Round of applause for Vidya. Thank you, sir.